Right, let's just jump straight into it. We're turning the emotional roller coaster of that whole NEET paper cancellation into a hyper-focused, super high-yield kinematics revision for this explainer. Look, if you've been feeling stressed out, overwhelmed, or honestly just exhausted by the news cycle, it's time to hit the reset button. Today, we're taking control back by focusing on literally the only thing we can control right now, our physics prep. I know you're super disappointed about the leak and the cancellation. But here's the thing. We have got to wipe that negativity from our minds. Seriously, we can't let exam drama dictate our future. So let's mentally reframe that May 3rd exam as nothing more than a mock test. It was just a dry run. Any mistakes you made, well, those were just practice errors.
Because think about it. We've just been handed a massive break, a literal second chance, and it is absolutely time to use it to our advantage. How many times have you walked out of an exam room just kicking yourself, wishing you had like one more month to revise, or wishing you remembered that one critical formula? Well, you actually have that time now. This is a crazy rare opportunity to bridge that gap between the score you got and the score you actually need for your dream medical college.
Now, my personal estimate, just based on how these massive administrative things usually go, is that we have roughly 1.5 to 2 months until the retest. Even if they try to rush it, organizing a whole nationwide exam takes time. And that is plenty of time for a massive comeback if we work smart. We aren't just going to study hard, we're going to study strategically, starting right now.
Okay, so here's our quick roadmap for today's explainer. 1. The comeback mindset. 2. Vectors and displacement. 3. Calculus and kinematics. 4. Mastering motion graphs. And 5. Equations of motion. Let's make absolutely sure your fundamentals are bulletproof. Starting with Section 1, Vectors and Displacement, the core strategy. So before we get bogged down in heavy formulas, we have to fundamentally lock in the difference between distance and displacement. Because you know it, examiners absolutely love to trick you here. Distance is an ongoing tally. It's always positive, it's always increasing, just the total path you covered. Displacement, though, that is strictly your final position minus your initial position, the shortest straight line from A to B. And yes, it can absolutely be negative. Mixing up speed, which uses distance, and velocity, which uses displacement, honestly, it's one of the most common, totally avoidable errors. Let's actually look at this in practice. Say a spacecraft moves from checkpoint P to checkpoint Q, and we need to find the net displacement vector. We just simply subtract the initial position vector P from the final position vector Q, right? So 7 minus -3 gives us 10i, 9 minus 5 gives us 4j, and 14 minus 2 gives us 12k. Boom. Just like that, we have our exact displacement vector, 10i plus 4j plus 12k. But the exam question usually asks for the shortest distance traveled, right? The magnitude. So finding the magnitude of that vector, taking the square root of 10 squared plus 4 squared plus 12 squared, that gives us the square root of 260, which means the shortest distance traveled is approximately 16.12 kilometers. Keep your calculations clean like this, and you won't drop those easy, low-hanging marks that make us all kick ourselves later. Moving on to Section 2, Calculus in Kinematics, the 120-degree problem. Okay, when dealing with circular motion, so many students just panic. They miscalculate the total distance or completely botch the vector subtraction. It is such a classic trap. Let's break it down simply. Imagine two position vectors, both magnitude r, separated by an angle of 120 degrees. To find average velocity, we first need total displacement. The shortcut formula for the magnitude of the difference between two equal vectors is 2r sine of theta over 2. So 2r sine of 60 gives us a displacement of r root 3. Next up, time. Time is just distance over speed. The distance here is the arc length, theta times radius, or 2 pi r over 3. Divide that by our constant speed of pi, and we get a time of 2r over 3 seconds. By just patiently dividing our displacement, r root 3, by our time 2r over 3, we safely arrive at 1.5 root 3 meters per second. No careless errors. Easy. All right, Section 3, Mastering Motion Graphs, the number line masterclass. Let's tackle what's basically the ultimate test of your kinematics understanding. We're using the position time equation, x equals 3t squared minus 24t plus 5. When they hand you an equation like this and ask for total distance, alarm bells should be ringing. It's a trap. You cannot just plug in the final time and call it a day. Here's the secret to this.
Whenever you see a negative sign in a position equation, it forces us to check if the velocity ever hits 0. So we differentiate position to find velocity, getting v equals 6t minus 24. Set that velocity to 0, and we see the particle comes to a complete, dead stop at exactly 4 seconds. Differentiating one more time gives us a constant acceleration of plus 6 meters per second squared. What this tells us is the particle was moving in the negative direction, decelerating, until it stopped at 4 seconds and then started accelerating back in the positive direction. It literally turns around.
And because it turns around, we absolutely have to map this journey visually to find the true distance. Drawing a quick number line is a foolproof way to do this. We plug t equals 0 into our equation. Okay, we start at a position of plus 5. Then we plug in our turnaround time, t equals 4, and see the particle traveled all the way back to negative 43. Finally, at t equals 6 seconds, it's moved forward again to negative 31.
This brilliantly illustrates exactly why distance and displacement are so fundamentally different. Our displacement is just final minus initial. Negative 31 minus 5 gives us negative 36 meters. Done. But distance, that's the whole exhausting path. From 5 to negative 43 is 48 meters traveled. Then, from negative 43 back to negative 31 is another 12 meters. Add those up, and our total distance is actually 60 meters. If you would just use that displacement value to find average speed, you'd be totally wrong. Translating all this math into visual graphs gives us, massive clarity. For our position time graph, because our t-squared term is positive, we get this beautiful upward parabola, dipping all the way down to a vertex at 4 seconds before rising back up. Our velocity time graph? That's just a straight line, starting at negative 24, crossing the 0 axis at 4 seconds, showing that constant positive slope, which is our acceleration. But what about the distance time graph? Well, remember, distance never, ever decreases. So it acts like a mirror. That initial downward curve of the position graph, it gets reflected strictly upward, representing distance continuously accumulating. Section 4, Equations of Motion, the quickfire. To wrap up the technical side of this review, let's look at your absolute bread and butter, the SUVAT equations. You obviously have to memorize these standard formulas. V equals U plus AT, S equals UT plus half AT squared, and V squared equals U squared plus 2AS. But here is the absolute most crucial point, and it's literally where smart students lose marks every year. You must remember the critical warning. These formulas only work if your acceleration is completely 100% constant. If acceleration is variable at all, you have to throw these out and fall back to the calculus methods we just talked about. Let's apply this to a super common exam scenario. A plane landing at 144 kilometers per hour that comes to a stop within 400 meters. First rule of NEET physics, always watch your units. We immediately convert that 144 kilometers per hour into meters per second by multiplying by 5 over 18. That gives us a nice clean 40 meters per second. Our final velocity is 0, obviously. Using our third equation of motion, 0 equals 40 squared plus 2 times acceleration times 400. Solve that out, and we easily get a uniform retardation of negative 2 meters per second squared. Now, what if the exam asks how long it took to stop? We just quickly pivot to the first equation, V equals U plus AT. 0 equals 40 minus 2t. Plug that in, and it gives us exactly 20 seconds for the plane to come to a complete halt. It's simple, it's precise, and it's fast, which is exactly how you need to be operating on exam day. Okay, we've covered a ton of ground today, from complex vector subtraction to calculus-based turnarounds, right through to those constant acceleration shortcuts. But honestly, the most important lesson today isn't on a graph. I really want you to leave this explainer energized. Completely ignore the exam drama. Tune out the noise, focus entirely on the incredible opportunity sitting right in front of you. Stay away from the rumors, and seriously, don't waste your energy being angry. Just be glad for the extra time. You've got your kinematics strategy totally locked in now. But remember, this is just phase 1. You need to apply this exact same rigorous, high-yield turnaround strategy to projectile motion, friction, work and energy, Newton's laws, the whole syllabus. The runway is clear, so the ultimate question is, how are you going to execute the rest of your comeback to secure that medical seat?